Motamot, a novel dataset for Bengali political sentiment analysis, has been introduced in this study. It comprises 7,058 instances annotated with positive and negative sentiments sourced from diverse online newspaper portals. The research explores the effectiveness of pre-trained language models, PLMs, and large language models, LLMs, in capturing complex sentiment characteristics in Bengali political sentiment analysis. The authors evaluate the performance of various PLMs, including BanglaBERT, BERT Base, XLM-RoBERTa, mBERT, and sahajBERT, alongside LLMs such as Gemini 1.5 Pro and GPT 3.5 Turbo. They explore zero-shot and few-shot learning strategies to enhance their understanding of political sentiment analysis methodologies. The findings highlight BanglaBERT's commendable accuracy of 88.10% among PLMs. However, the exploration into LLMs reveals even more promising results, with Gemini 1.5 Pro achieving an impressive accuracy of 96.33% through the adept application of few-shot learning techniques, surpassing the remarkable performance of GPT 3.5 Turbo, which stands at 94%. This study addresses the scarcity of thorough research devoted to political sentiment analysis, particularly in the Bengali language. The authors investigate public sentiments about politics on Bangladeshi online newspapers during elections, analyzing a large amount of content to understand people's perspectives on political issues and the emotions conveyed by political parties. The Motamot dataset is a comprehensive resource for political sentiment analysis, providing valuable insights for both political parties and voters by understanding the views and opinions expressed by individuals, as well as the sentiments of political parties, allowing them to make informed decisions. In a comprehensive study on political sentiment analysis in the Bengali language, researchers evaluated the performance of pre-trained language models, PLMs, and large language models, LLMs, on a dataset of 7,058 labeled instances. The models tested included BanglaBERT, BERT Base, XLM-RoBERTa, mBERT, sahajBERT, Gemini 1.5 Pro, and GPT 3.5 Turbo. The results show that large language models generally underperform state-of-the-art fine-tuned pre-trained language models across most evaluation tasks, revealing significant performance disparities among LLMs. This suggests that current LLMs are not well suited for addressing low-resourced language tasks in Bengali, particularly in zero-shot scenarios. In contrast, few-shot learning is shown to outperform PLMs, highlighting its potential as a more effective approach for Bengali political sentiment analysis tasks. Notably, few-shot learning does not exhibit hallucination, which occurred in zero-shot scenarios. This study also reviews related works in sentiment analysis, including semi-supervised approaches for market sentiment analysis, hybrid models for student feedback, e-commerce sentiment analysis, and NLP-based analysis of Bangladeshi food delivery app reviews. The background study provides an overview of pre-trained language models on Bangla, including Electra Base, BERT Base, Albert Large, and RoBERTa Base. These models have demonstrated state-of-the-art performance across diverse downstream tasks, and their efficacy is briefly explored in the context of Bengali language processing. Overall, the study highlights the limitations of current LLMs in addressing low-resourced language tasks in Bengali and suggests few-shot learning as a promising approach for political sentiment analysis in this language. The research paper focuses on large language models applied to the Bangla language, specifically discussing GPT 3.5 Turbo and Gemini 1.5 Pro. GPT 3.5 Turbo is ideal for tasks requiring specific formatting or outputs, such as creative content development, due to its fine-tuning capability and broad context window of 16,385 tokens. Gemini 1.5 Pro, a multimodal model, excels in processing text, audio, and video, with a substantial input token limit of 30,720 and output token limit of 2,048. The paper then delves into the creation of the Motamot dataset, compiled from online newspapers focusing on political events and conversations during Bangladeshi elections. The dataset comprises attributes such as source link, newspaper name, published date, headline, short description, and sentiment. The annotation process was manual, with 6 student annotators providing emotion labels after careful analysis of each article's content. The annotation guidelines were extensively developed to ensure uniformity and precision in sentiment labeling. The dataset statistics are presented in Figure 1, showing the composition and scope of the dataset, with precise statistics across multiple subsets. The dataset is divided into 3 categories: train, 80%, test, 10%, and validation, 10%. The Fleisch-Kappa Iterator reliability coefficient was employed to evaluate the annotation approach's consistency, achieving a high Kappa score of 0.87, indicating strong agreement among annotators. The paper also discusses the challenges faced during data collection, including biased news reporting, sentiment ambiguity, and language variations. Quality control measures were implemented to mitigate these challenges' impact. The dataset includes only positive and negative sentiment labels, potentially limiting sentiment analysis granularity. Gender, location, and political biases were considered during annotation, but addressing them comprehensively remains challenging. Figure 1 illustrates the sentiment distribution across the train, test, and validation datasets, showcasing the analysis of political sentiments using the Motamot dataset, a CSV-formatted dataset compatible with various research tools and platforms. To implement political sentiment analysis using pre-trained language models, PLMs, the approach involves preparing the data, model fine-tuning, and performance evaluation. The dataset undergoes text pre-processing, including normalization steps specifically designed for Bengali text, to ensure compatibility with PLMs. Fine-tuning involves training initialized PLMs on the political sentiment analysis dataset using transfer learning techniques, with the objective of minimizing cross-entropy loss. The AtomW optimizer and cross-entropy loss are employed, and hyperparameters such as learning rate, batch size, and epochs are adjusted to optimize performance and prevent overfitting. The performance of fine-tuned PLMs is evaluated on a held-out test set using accuracy, precision, recall, and F1 score as evaluation criteria. For hyperparameter optimization, Table I provides detailed guidance to enhance model performance. Table 2 presents comprehensive performance metrics on the effectiveness of fine-tuned models for political sentiment analysis tasks. Additionally, the study explores political sentiment analysis using large language models, LLMs. A subset of 300 data points from the Motamot dataset is randomly selected to assess the effectiveness of zero-shot and few-shot prompts. The data selection focuses on instances with a short description column containing more than 25 words, with each label category comprising 100 instances. A prompting template is designed to direct text generation, specifying input parameters crucial for task customization and output refinement. Figure 2 displays zero-shot prompting with the Motamot dataset, highlighting Gemini 1.5 Pro's zero-shot accuracy in political sentiment analysis without explicit training. The analysis employs a zero-shot prompting technique to examine the political sentiment of Bangla text, focusing on meaning and sound. It determines the sentiment as positive or negative based on a 5-shot scenario, where the model is provided with 5 labeled examples. The results indicate a negative sentiment for the given text, showcasing the model's ability to accurately discern political sentiment with minimal training data. The authors present the performance of various pre-trained language models in political sentiment analysis, showcasing their strengths and limitations in sentiment prediction. Figure 3 displays the confusion matrices for BanglaBERT, BanglaBERT Base, XLM-RoBERTa, mBERT, and sahajBERT, demonstrating their classification accuracy across sentiment categories. BanglaBERT outperforms the other models, achieving an accuracy of 0.8810, precision of 0.8765, recall of 0.8799, and F1 score of 0.8780. The authors emphasize the importance of crafting well-organized prompts for political sentiment analysis, highlighting the need for clear instructions, context, and focus on pertinent language components and relationships within the text. They also explore the underlying causes of zero-shot collapse, attributing it to insufficient pre-training data, biases in the training dataset, and the complexity of sentiment analysis tasks. The authors discuss the benefits of few-shot learning in political sentiment analysis, enabling model adaptation and generalization to new sentiment classification tasks with minimal labeled data. They examine the advantages of 5-shot, 10-shot, and 15-shot learning, which allow the model to learn key linguistic patterns and features relevant to sentiment analysis while reducing reliance on large annotated datasets. The evaluation of prompt efficiency in political sentiment analysis involves assessing model metrics such as accuracy, precision, recall, and F1 score on a held-out test set. Control settings for large language models, LLMs, include temperature 1.0, top P 1.0, maximum tokens 256, frequency penalty 0.0, and presence penalty 0.0. Results of zero-shot and few-shot learning approaches are presented in Table 3, showcasing the performance of 5-shot, 10-shot, and 15-shot learning with GPT 3.5 Turbo and Gemini 1.5 Pro model LLMs. These results demonstrate the efficacy of LLMs in handling various shot learning scenarios, outperforming traditional methods in political sentiment analysis. LLMs consistently achieve excellent accuracy, precision, and recall, indicating their ability to capture nuanced sentiments and accurately detect significant political thoughts. To enhance transparency, trust, and accuracy, techniques like chain-of-thought prompting and two-stage prompting can be implemented. Engaging humans in the evaluation loop can also provide vital input for improving model performance and identifying biases. Future research directions include fine-grained sentiment analysis, multimodal analysis, and explainable AI, XAI, techniques to enhance granularity, interpretability, and trustworthiness of political sentiment analysis models. The paper presents a novel approach to quantum error correction, leveraging the principles of quantum entanglement and superposition to protect quantum information from environmental noise. This methodology, known as the surface code, is based on a grid of qubits arranged in a specific pattern to encode, detect, and correct errors without disturbing the quantum state. The surface code operates by using ancillary qubits to detect bit flip and phase flip errors, which are common types of quantum errors. These ancillary qubits are arranged around the data qubits, forming a lattice structure that allows for the detection of errors through measurements. Once an error is detected, correction operations can be applied to restore the original quantum information. The authors demonstrate the efficacy of the surface code by simulating its performance under various noise models. They show that the code can effectively correct errors even when the error rates are relatively high, making it a promising approach for practical quantum computing systems. A key advantage of the surface code is its fault tolerance, which means it can maintain the integrity of quantum information even if some of the qubits or operations fail. This property is crucial for building scalable and reliable quantum computers. The paper also discusses the challenges of implementing the surface code in real-world quantum computing systems, including the need for high-fidelity qubits and precise control over quantum operations. Despite these challenges, the authors argue that the surface code offers a promising path forward for achieving robust quantum error correction in future quantum technologies.